Okay, so we have majority of people here, and I will start. So welcome to a very first workshop organized by Optics11 Live. My name is Nelda, and I am a product manager of part1, a high throughput nanoindenter, but I also provide application related support. Because before I started to work in Optics11, I did a PhD in biomechanics where I used similar indenter to Chiara to characterize brain tissue, glial cells, and chicken embryos. While working at Optics11, I also got a chance to measure all kinds of materials. So I'm happy to share with you all the best practices. And together with me are my colleagues. I'm not sure, I hope you can see them. So it's Chris, Nikolai, and Priya. So they can answer your questions that arise during the workshop. So you can just use the Q&A option for the questions, because then we can just answer them there and kind of keep track. If you have any other comments during the presentation, like you have a tip or you want to share the experience, you can just write in the chat window, and then we can look at it later as well and learn from your experiences. So the schedule is quite tight. I have 92 slides and I have no idea how long it's going to take. So I will launch a poll, the first one. I also have, I think, 9 polls just to ask you different things. So the first one is, how long would you like this webinar to be? So what we can do, if you think 1 hour is enough, then after 1 hour we can just stop and just schedule another session of the workshop, let's say in 2 weeks, to continue with the material. If you think that you can sit 2 hours, then that's great, but let's see what majority of people chooses, and then we can decide. I also didn't know. So I see majority is going for 1 hour. Yes, okay, that's very short. So, but that's fine. Let's do the first hour, and then we can stop, and then maybe 1 hour, 15 minutes. Let's see how it goes. And then we can do another session next time, because there's quite some things that we want to discuss with you. Okay, so the workshop consists of 2 parts. So in the first part, I want to introduce you to the news. So system upgrades, software updates, and new system and new probes. And in the second part, which is the longest, actually, it's all the tips and tricks regarding sample preparation, how to choose the right probe, how to calibrate, DIP modes, DMA, and some fitting options. And the third part, very short, just we want to share with you our vision of the future of mechanical testing, and maybe get your feedback about that as well. The first part. On our website, you can find the links to publications based on different categories if you haven't seen it before. We have almost now 200 publications where either PUMA or Chiara was used to characterize various samples. So you can find a lot of information in these publications, just see how others perform the experiments. And yes, so we will reach 200 hopefully at the end of this year. Regarding publications, it's important to know that we changed, our department changed the name. So Optics11 has 2 departments. We have industrial sensing, which works with health monitoring of, let's say, buildings, trains, and so it's very different application, but it's using the same sensors. While we are, so they keep the name Optics11. Well, we added a live at the end for life science applications. So please, if you reference us in the publication to add live, so that others who read it can find our company rather than industrial sensing. Now, I would like to show for all the users who has purchased the instrument before 2019 September, the available upgrades. We would like everyone to have our newest hardware, as it makes a huge difference for the user experience. We don't make profit out of this upgrade. The price is very reasonable. We just want everyone to have this good experience with using the system. Now, the main and most important difference is that the stages, so X, Y, Z stages, are operating now in closed loop. Now, what does it mean? It means that we can increase fine surface speed and make it continuous. So it's not moving in steps like before, it's just a continuous movement. So it's much faster, also much more precise. It has precision of 80 nanometers. That's also important for mapping in X, Y directions, because you can very precisely come back to the same location. Also, the movement is silent. You're probably annoyed, like we were, by this very high frequency stepping sound, so that's gone. And funny enough, now when it's gone, we actually miss it because we don't know if the stages are really moving or not. You have to listen very carefully. So this is a huge improvement for the fine surface experience. We also have a software update. You can also get new software for the old system if you have interferometer version 2. So you can check the bus if that's possible for you. It has improved user interface. You can configure multiple experiments one after another. You can save them and reload it, so you don't need to remember all the parameters. And as I mentioned, the data viewer is available to everyone. You can just download it and use it for the data obtained by any of the instruments. Piezo has also changed. Before we had 20 micrometers, now it's 100 micrometers standard, so it's longer range. That's very useful if you want to sense deeper into the sample. Also, it allows to work around adhesion, so you have more range to get out of the when it's sticky. And additionally, you also get the topography information, so you can really get the height profile. So I have here a few examples. This is a monolayer. I hope you can see this one cell here, at least the cell soma, and that's another one, but it's in a monolayer. So I mapped this area 12 times 12 metric scan, and as a result, I get something like this. So this is very stiff, and this is the softer area, and then, okay, this is stiff, but probably because these are very thin areas, and I'm not really indenting on the cell cytoplasm, but I'm actually sensing the substrate. So now, if we look at the topography, that gives you exactly the information, how the surface looks like. So this is very low, and this is higher, and you can even obtain the height of the cell if you need such information. That's also useful for hydrogels. So for example, here I use Petrosoft, which was dry. When I added some medium and started to perform the metric scan from the side, and then what you can see in topography that the surface position moves from 0 relative position up to 310 micrometers. So that's how much the hydrogel increased in thickness while it was swelling. And you also can see why, that explains why the stiffness changed from stiff when it's dry to a softer one when it uptakes some water. So topography is quite handy. As you probably know, it's also quite tricky to use the top camera in liquid when working with Puma. You actually need to fill the whole Petri dish with a medium and add a glass slide on top. So then there's no air gap, and then move the manual stage down until you see the sample in focus. From there on, you can use motorized stages to find the surface and so on. Of course, the resolution of this top camera is not great. So probably some of you already have, but for others that we have inverted camera module, and this is the new camera that we use, which actually has quite a good resolution. You can image down to 50 micrometer size features. So we have some, so here you can see the sphere, for example, and we have some people even using Puma to measure cell monolayers because they could actually see such structures. You can also use the camera from the side if you want to see the tip or the sphere is still there. So you can use it in both ways. Also, if your application has changed to where you need higher imaging resolution, you can get a Chiaro head, which can be connected to the same controller and interferometer as Puma. So you can expand your applications. In addition, that's something new that we can perform now, also lateral indentations with Chiaro. So here you can see that the piezo is actually facing to horizontal direction. And then here the probe is indenting on the side of this glass Petri dish for calibration, for example. And here we have a piece of Petrisoft and we're just indenting on the side. And you can also imagine that this can be done on single cells. So if you are interested, you could also get this kind of configuration for some interesting experiment. Now, we also provide, like before, on-site and remote training. So if you are new in the lab or the person who was in charge of one of our indenters has left the lab and didn't train you, and we can provide it used to be on-site training, now it's remote training. So yes, we can provide such a service. Or for example, if you have to measure a new sample, which is difficult and you're not sure what kind of indentation profile to use, what kind of probe to pick, we can also help you with that. It is also important to note that piezo and stages do wear out. So if someone has the system already for 5 years and hasn't replaced any parts, I would be a bit concerned. It is like a car. Once in a while, you do need to fix some parts. They wear out. So you have to maybe replace oil and so on. So we recommend considering the warranty and also software update packages. And yes, so probably some of you already saw, but I would really like to introduce to you just at least that you know what it is and what it can do. It's our newest system, Pavone. So we made a new probe design, which is able to measure inside the well plates, inside 96 well plate. As you can see in this image, I'll show you better afterwards. So in Pavone, you can mount 2 well plates, and then the system can move automatically between the wells, which allows very high throughput of measurements. The system also has inverted microscope on board, and it's integrated, meaning that you can just choose in the field of view where you want to measure, and then the probe will just go to that area and measure that. That's in contrast to Chiaro, where you have to move everything manually to align the tip with the sample to do the measurements. It also has temperature control on board, so your samples will be happy at 37 degrees. And we have other options for imaging, so fluorescence and confocal, which is on our roadmap and will be launched probably next year, so we can do even more fancy mechanobiology experiments. I have a short video just to show how it looks like. Yes, so we opened the lid and we had 2 well plates in the screen. We can just pick to which well we want to go. Let's say this is, we choose manually to which well, and then the stages moves to the well that we want, and then back or anywhere where we like. And here you can see a little better the probe. So it's very thin and long, and it fits inside the well and has enough space to move around the 96 well. Now high throughput, so how high is the throughput? I put here in the table that if you want to do one static measurement in a well for 96 wells, it will take 10 minutes. If you want to perform a small metric scan, it would take 55 minutes. So that is quite fast. Of course, for dynamic measurements, as you know, everything takes longer because you have to wait for this longer relaxation. Now, this is the configure experiment is similar to the new software Puma and Chiaro, where you can put all the experiments one after another. So similarly in Pavone, you can also add also the movement in between the wells. You can add imaging steps. So you can synchronize image and do indentation. You can also add cleaning steps. So it's really programmable experiment of the whole well plate, or even 2 well plates if you have that many conditions, that many samples. And I here have example on hydrogels. So this is, you probably know, the Matrogen company, which provides these well plates with hydrogels with ranging stiffness for cell culturing. So for example, they have from 200 Pascal up to 50 kilopascal. And then we just took that well plate and measured the actual stiffness in one go, fully automatically. Now, if you have single cells or organoids, for example, here you can see how the movement is done. So I pressed on the screen and then pressed move to point, and then indenter just goes to the area I chose, and then we find the surface, and then we can perform indentation, and then you will see very quickly the result. Yes, so it's finished. We have 200 pascals approximately. It was very sticky as well. Now, if you have multiple objects, such as single cells, you can use the coordinate list. So you press on the screen with the mouse, multiple coordinates that you would like to measure, and then you load these coordinates into the experiment, and then the measurements will be just performed in each coordinate that you chose. So it's, let's say, the semi-throughput. In the future, we would like to, we are investigating if we could have, let's say, cell recognition, so that you don't even need to press on the screen. But for now, still the speed is way improved. One measurement, including the movement of the stages, takes 7 seconds. So you could measure 550 cells per hour, which is a lot. You will have a lot of data and great statistics out of it. So applications are very broad. You can phenotype whole well plates of cells treated with different drugs, or you can assess reproducibility of your hydrogels if you want to scale up the production, for example. In addition, if you get environment control and sterility, then you can even run multiple day experiments. And if you add confocal module, you can combine directly structural and functional information with mechanical data. So this was about Pavone, which we believe will be very widely used in the future. So we wanted to share with you and also ask, I'm launching the poll, if you would have a Pavone, which features would be the most important for you and for your research, if you would have such an instrument in your lab instead of Puma and Chiaro? Because of course everyone has very different applications, so and there's so many ways we can improve Pavone. We can add modules, we can add imaging, different control, we can even use different sensors. So we are still exploring where the instrument would find the best fit and for what kind of experiments it will be needed. Okay, so I leave a poll, but then I proceed. So we have 3 types of probes. You are familiar with these two. So it's either single ferrule or double ferrule. And this is the newest one, Pavone probe, and it can measure the well plates, and you can also use it with Puma and Chiara. So that's very handy. You need a much smaller volume of a medium, and maybe it's a more convenient format to measure in the well plates. So that will be possible. We will officially put Pavone probes on the web shop from January 1st. So yes, if you wait a little bit, you will see it on our web shop. Yeah, so here you can see just the same probe in Puma, and you can just put the well plate on Puma as well. Another thing I wanted to point out is that the smaller tip sizes are mounted on the extension rod, as you can see for the 25 micrometers. And I'm thinking if you actually see, oh, now I have a laser pointer. Yes, so they are an extension rod for all the smaller tips, and that's the same for the Pavone as well, because that's quite handy when you have samples with irregular shape, as I will show you later. Now, these are the Pavone probes in blue, which will be available. So we won't have a stiffer range. We don't have the stiffer range yet, but we will have in the future. But now we have the most popular stiffness, I think, for many applications. And this is our web shop. So I'm not sure if all of you seen it, but you don't have to ask us anymore which probes we have and which probe, send us the list what you want to order. You can just do everything online. So just pick the probes that you like and make the order in an automatic way. And finally, the last news is the patch cord. So if you haven't ordered probes in a long time, then you haven't seen it yet. What it does, it keeps the fiber of a probe shorter. However, it does bring a challenge that we cannot directly check whether the probe is broken or the patch cord is broken. So in order to, because now we have two parts instead of one. So in order to check if the patch cord is broken, you need to then put multiple probes and see if all of them are not giving any signal, then it means that the patch cord is broken. You can send us a quick email and we send the patch cord for free. And for someone who don't have it yet, you will automatically just get the patch cord together with your next order. Yes, and then I have a question about the probes. So we have a list of the standard probes that we do make. But there are, of course, other probes that we could make with different characteristics. So I listed here the options that we don't have yet. And I'm interested if any of them would be needed for anyone. Yeah, so if you think that you're fine with what we have available, then don't put anything there. But if you think, yeah, if you need something else, then just choose. I quickly look through the questions. Is this webinar recorded? Yes, it is. And I think I will put it on YouTube as unlisted, so you can also watch it afterwards. Yes, about Pavone, are you aiming for compatibility with established confocals from Zeiss or Leica, or you build your own? No, so we are going to use confocal.nl, rescanning confocal microscope. That's a Dutch microscopy company. You can check their specifications. So they have super resolution by using a trick. So we are planning to integrate. We have already started to integrate the systems together. Yeah, so you can see all the features of their system. Okay, I'll continue and then answer the other questions later. So now the second part, tips and tricks. So first, as you already saw in the chat, I send 2 links. One link is to some additional documents that we have available. They are more internal because we are constantly improving them and we're writing them. So if you didn't have them, then you can download. And also on our website, we have the newest manuals and the newest data viewer manual, as well as the newest data viewer. So please, you can use these resources. There's a lot of information there. Actually, everything you need you can find in these manuals. There are also some videos on the website, for example, how to do basic measurements. I've also seen that some groups have made their own personal group videos, so that's very nice and encouraging. If you have some of these videos, please share with us. We will be happy to advertise them as well, so that others can benefit. Now, the sample preparation. The 2 main techniques that we use is the auger mounting and chamber with the harp. So here you can, for example, see how auger was used to mount chicken embryos, but it can also apply to any hydrogels which are in a regular shape, even tissues, something on a membrane, like the transfels. You can also mount it on auger. The way it's done, we warm up the auger, and then we pipe it in the Petri dish, a thin layer. And then you add your sample on top, and then you can even make a little ring around. So that's what you can see here to even clamp it better. In this case, the sample is so thin that we use filter paper to handle it. So you can think whether you could also use it. It's very handy. We use it all the time and very simple to make it. Important is to use the auger, which is stiffer than your sample. The auger is very soft. What will happen is you are not going to indent the sample, but you will indent the auger through the sample. So you can also just characterize the properties of auger and then compare to your sample and then choose a stiffer auger. It needs solid support. The other technique, very handy for tissues. So if you have thin tissue slices, we use these 3D printed chambers. You can either buy them from a company or you can just design your own in 3D print. At the bottom, you can mount the glass slide. And then on top is the slice. And then we use the harp, which you can also purchase from the company, to push it down to hold it at the bottom. The glass can also be coated with something that makes it sticky, so that when the tissue gets in contact with the glass, it kind of adheres. And that's very important for mechanical characterization. If the sample is floating, your measurements are not going to be right, your stiffness is going to be wrong, and I will show you exactly how that looks like. So here I have the same brain slice. I'm using OCT, optical coherence tomography, to see the slice in a cross section. So this is just the air. So this is upside down. Actually, this is the air. This is the glass slide, and this is the tissue and the sphere. So indentation sphere. Now you see there's a gap between the glass and the tissue. And if you do indentation on such a not well-mounted sample, the curve looks like this. So you see it doesn't follow Hertz model. We have one bump and then the second bump. Because first bump, you are just pushing the sample down until it actually touches the glass, and then only you start to perform indentation. So you cannot use this curve to analyze the data. Yes. Now in second case, I had only a very small gap between, you can barely see it. Even in that case, if you do the same, first you have one slope and then a higher slope. So the first slope is just pushing the sample towards the glass. And then once it gets in contact with the glass, then you have a proper curve. And the final, of course, if you have a nice mounting of a sample, your Hertz, your curve looks perfect. So it kind of gives an indication. So sample mounting is very important. It shouldn't be floating. So you also need to know the shape of your sample. So for example, imagine this is some kind of hydrogel with some cells inside and has some kind of round shape. So if we measure on this side of the sample, there's no issue for the cantilever to bend, nothing is going to touch it, all good. However, when we reach this area, we are on the other side a little bit. When we move the piezo down by this distance, we will start to push into the sample with the base of the cantilever. What it's going to do, it will break the probe. Maybe, maybe not, but it's not good. Also, your load indentation curve would look strange, so it will give indication, okay, something is wrong there. And of course, if we are even further, then you cannot even find surface, because instead of bending the cantilever, you're touching on the base of the cantilever. So there is signal, but the signal is strange. And that's because, yes, you're not indenting. Well, actually, in this case, you will find the surface still correctly, but only after you indent a bit deeper, you see the irregularities. So you always need to know the shape of the sample and ideally measure on the side where it's free. If you want to measure the other side, you need to rotate the sample and measure from that side safely, or you need to use a bigger sphere. So then if that's possible. Also using the small tips with extended rod helps because you have larger distance before you would hit with the cantilever. It just makes the extension here. So that's why we made it like this. Now also the probe is actually on a 2-degree angle, so that gives a little bit more space before you will hit with the cantilever. So we do try to help there. Yes. Now, how to choose the tip. So you will find the document and the attached information. I will just quickly go over these very important details. So, okay, what you see here, I tried to draw a brain tissue of a thickness of 300 micrometers. And then we have 3 probes, 10 micrometers, 90, and 250 micrometer radius. Now, the first condition, and that all arises from Hertz model assumptions. First condition, that your indentation depth shouldn't be more than 5% of the sample thickness. Now, the sample is 300 micrometers. That means you cannot indent more than 15 micrometers. Now, the second condition is that the indentation depth should be less than 16% of the tip radius, at least for the standard Hertz parabolic model. Now, what does it mean for these 3 spheres? It means with the small sphere, we can only indent 1.6 micrometer indentation depth. So for the larger one, deeper. And now for very large one, although we can indent up to 40 micrometers, we get limitation because of the thickness, which was 15. So with the large sphere, we can only indent 15 micrometers. This is also the contact radius. It's calculated by the square root of indentation depth times the radius. I draw it here. Why it's important? You need to consider, yes, let's say the step size, like the area that you are going to sense. So for example, this is the brain tissue, hippocampus, and in the lines you see different regions, and different regions have very different dimensions. However, if we really want to measure this region, for example, which is very thin, if we use this large area, we are going to not measure only that region, but also the surrounding ones. So for sure, this big sphere, this indentation depth is too big to measure the sample. Now, the smaller sphere is better in this case. Of course, we could also go for the smaller sphere, which you don't even see, but we also have to consider the surface roughness. So tissues are usually sliced, and slicing makes the surface rough. It's also damaged. So here you can see the drawing of such a surface. So if I use the large sphere, actually then I sense this the least. Well, if I'm using the small sphere, I'm just going to measure this very broken dead cell layer at the top. So it's also not ideal. So you have to consider all these different things before you choose the tip size. It's a lot, but it's doable. Now, the next thing I would like to show is Excel calculator. So I hope you can see the Excel now. I have to close these down. Yes, so in this calculator, you can see, yeah, so it's also attached in the files that I sent. So here you can choose the radius that you use, for example, 50 micrometers. This is indentation depth that you would like to measure at, let's say 5 micrometers, and the probe stiffness, so 0.25 Newton per meter. And then this is the minimum threshold, let's say the minimum amount of cantilever bending that your system is able to resolve, which depends on the system noise level. So the more quiet the system, the lower this number can be. And this is the maximum bending of the cantilever, so we recommend the maximum of 30 micrometers. And what you get as a result when you fill all these details is the minimum Young's modulus that you can measure and the maximum Young's modulus that you can measure. So for example, you can now play around. Let's say you have a sample which is 250 kilopascals, and you are not sure if you can really measure it with the probe. You can very quickly check. For example, if I change indentation depth to 1 micrometer, my range of what I can measure increases a lot. So at smaller depths, I can measure much more stiffness values. You can also see how this changes if I change the tip size. So if I use a smaller tip, yeah, then I can measure even more because there's more stress applied in the same area. So this I find very handy, and before doing any measurements, I usually play around and see what can be done, which tip sizes I can use, which stiffness, and so on. So I recommend using it. Okay, so now about the probes. So probes need to be pre-wetted, as you all know, because we do not want to trap an air bubble. It can also happen that cantilever is stuck to the fiber. You can gently touch it with the tissue to release it. Also important always to clean and dry your probe after the use so that it does not dry in this stuck position. Now, any of these things can happen, but luckily you do have an interferometer, which is basically your eyes. If the cantilever is stuck, you won't have a signal when you do the wavelength scan, or you lose the signal during the measurements because that happened. If you have a bubble, you will have very noisy signal. So all of that, yeah, so interferometer just helps you to see what happens. And the best practice is, yes, always to run a lot of liquid over the probe so that it detaches, yeah, and it's in a good position. Yeah, so for the new users, I will just quickly explain the signals that I'm going to talk about further on. So the first one is the signals in the main screen. We have a piezo signal in blue, and the green one is the cantilever signal. Now you also have interferometer signals. So this one, the main measure signal is the same as this green one, but just an interferometer. Now when you indent on the sample, what you will see here is fringes. So the signal is not linear. What we measure is interference fringes. So when cantilever bends, you just see these, yeah, this kind of shape. Now, instead of bending the cantilever, you can also change the wavelength of the laser, and you will see the same fringes. We use that to assess the medium, to tune the laser parameters to the right ones so that we will have the best signal. And that needs to be done every time we put the probe into the medium. Now we can also look at this signal as it is fringes, it's in the soil signal. We can look at it in a circle. We call it demodulation circle. So whenever we are indenting, the signal moves clockwise, and when we are retracting, it moves counterclockwise. If we are not in contact with the sample, the signal is just stationary. Maybe you can see some noise if you bounce on the table. So yes, usually I look at the demodulation signal the whole time, and I know exactly what's going on with my probe. So if you don't do that, I recommend starting to do that. You will get used to it, and then it will be your eyes to what's happening with the probe. You won't need to try to look at it with the camera or something. You will just know what's going on. So then maybe it's good time maybe to look through the questions. Oh, they all has been answered. Yes, so I'll continue, and I see the question about geometrical factor. I will cover that in a few slides. So the wavelength scan, the first thing, we do need to pre-wet the probe. That's important. Then we need to do the wavelength scan in the measurement medium. Then we need to make sure that there's no meniscus. So if you only submerge the probe at 500 nanometers, then there will be like a little pile up, capillary forces, we call it meniscus, and that might induce force on the cantilever. Cantilever needs to be in completely neutral position without any forces on it during the wavelength scan. So yes, submerge the probe deeper into the medium so that it's stable. Also, you need to let the probe stabilize. I'll show later how the drift looks like. If you just submerge in the medium and you do the wavelength scan right away, you will get the wavelength scan. However, your signal is going to drift, and it will drift away, and the settings that you got will be wrong, and you will have issues. You'll have to redo the wavelength scan. Now you also need to don't have the sample, the probe in any contact. So as I said, it should be completely neutral position. So if you don't get fringes after the wavelength scan, you need to check the connector. It might be that it didn't click in. You also need to check the cantilever. I usually just lift the probe up, run some liquid over it, and put it back into the medium, and then try again. Maybe it was just stuck, or there was air bubble or something. So that's a very quick test. You can also run more medium over the probe when the probe is already in liquid. Kind of makes a flow over it. So if something is stuck when it was entering the medium, then this is going to help. If you still don't have any signal, then you can just take out the probe, dry it, and then run the wavelength scan in air and see if there is a signal. If there is a signal in air, then it means it should be signal in liquid as well. You just did there's something wrong with the medium and entering into the medium. If you still don't have any signal in the wavelength scan, do not proceed with calibration because you will break the probe. So these are my tips. And I have here example of, yes, so this is how the wavelength scan should look like. And if there's no good result, then yes, you get also a message that the scan has failed and please repeat. And we have multiple, it could be many different things that is wrong. I have them listed here. You can find in the manual. It could be anything. So we have to try to find where the issue is. Now, does this work? Yes. So here I submerge the probe in the medium and just observe the signal. So in the measure window. And now you can see that the signal is not stable. It's just going up and down through the fringes. So it's going up and then down. And this is the drift. So you cannot measure while the probe is drifting. You just need to wait a few minutes, maybe 3 to 5 minutes. The probe is adjusting to the medium, to the temperature. If you are, for example, just took the medium from the fridge and you put the probe in, it's going to drift until the medium warms up to the room temperature. Or it can be the other way around. If you bring the sample from the incubator, then it needs time to cool down. So it's going to drift. Now, and this is how it should look like. So I waited, I think, 3 minutes only, and then the signal is just in one position. It's not really going up or down. So that's how it should look like. Now, there's another trick regarding the, how to improve, how to decrease the noise level is by increasing the laser power. So for example, I did here the wavelength scan, and then I look in the details about the gain, offset, and range. And I see here that range is high. Now, of course, you see that the signal is not on the circle. That's because we didn't calibrate it yet. We only did the wavelength scan. The signal will be on the circle only when you do the calibration. So don't panic yet. That's coming. Now, the first thing we check is really if the signal is in high range. So if it is in high range, you can, what it means is that the gain is high. High gain is high noise. Now, we can decrease that by moving to another window and finding the power. So this is laser power. Probably the default laser power that you have is 6.31 milliwatts. Now you can increase it to the maximum one, to the 25, and then you repeat the wavelength scan, and then you will see that the range is low. And what it means is that the signal to noise ratio will be much better. So will be less noise and all the measurements will look better. So that's a little trick. So we are going to make this feature automatic, that the interferometer will just decide by himself that it needs to change the laser power. But until we have that feature implemented, then you will need to do that manually. Now the next step is to find the surface. We can find surface from calibration window, and this find surface should end up in contact with the stiff sample, so with the glass slide, for example, or glass petri dish. Actually, you need to make sure that this glass petri dish is clean, and also that the probe is clean, because that will influence, as I will show later. Now, if find surface step triggers early, you need to increase the threshold in options, or if you have old hardware, it's called sensitivity. You also can decrease the speed, because movement of the piezo also induces some noise, so you can decrease the speed. Or in old hardware, that's the step size, so moving at smaller steps gives less noise. And you can check manually as well the 1 micrometer steps if you're really in contact or not. Now, this is how finding contact looks like. As you can see here in cantilever signal, there's a little bump. So we found the signal. Let's say this is how it looks like in the old software. So you see the steps, and then when it finds the surface, and then it moves back up. Now, if you're not sure, you missed it, or you want to double check, you can just check manually. So what I did here, I moved down, and I see that there is a change in the baseline, and then I'm moving up, 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 and here I'm out of contact. So I continue to move up and the baseline doesn't change. It means I'm out of contact. So then I can manually just bring back the probe to the contact. So this is a good check if fine surface worked. Now the last step is calibrate. For that you need that the cantilever and piezo signal goes up at the same time. So that looks like this. So the blue line and the cantilever line goes up at the same time. If that's not the case, it means your fine surface step was not correct. So you need to go back and adjust the settings until you have the probe in contact with the sample after fine surface. Now the calibration distance should be around 5 micrometers. After calibration, you need to check the demodulation signal, that the signal is on the circle, not somewhere out. You can also indent on the glass afterwards and see if there's any indentation, if there's any relaxation in the curve. It means that something is dirty, either the probe or the sample. So if you have some indentation afterwards, just clean everything and repeat the procedure. And finally, the most important, check the G factor. So calibration, that's called calibration factor in the software. So calibration factor in the media should be equal to calibration factor in air, which is given on the box, divided by refractive index of the medium. Yes, so that's very easy. And you should be plus minus 0.1 in the range. If you are off, then yes, just clean everything and repeat the procedure. Yes, so now what is the calibration factor? I just wanted to quickly explain. So the movement of the tip takes place, at the tip. So that's where actual indentation takes place. However, the fiber reads out position of the cantilever here. Now that's not the same distance. The tip moves more than what the fiber sees. So this is called geometrical factor correction if we just take the ratio between these two distances. So during calibration, we do it on something very stiff, because then we know that how much the piezo moved is the real distance, and whatever fiber sees, that's that smaller distance due to the refractive index of the medium and due to the mismatch actually. So so based on that, we can calculate this geometrical factor. And then a few more tricks that I have is, so if during the experiments the signal went out because of the drift or something else, what you can do, you can manually tap on the system until you have one circle of noise, and then in here choose calibrate, and then continue tapping. So you're inducing one circle of noise. You continue that while it's in progress, and you see as a result, you have a signal back. So usually if you did calibration when at different temperature, then your signal will drift away and you need to recalibrate this demodulation signal. And as you saw, you can do that in 30 seconds, just simply tapping on the system or somewhere close to the probe, so inducing some noise, and then your signal is back on track. If the signal is out and you continue the measurements, what you will get is the wavy curves. Maybe you have seen that. So in the load indentation curves, the signal is not nice, but there's waves. That's because this demodulation circle is off, so the signal is wrong. That's why you get that. That can be fixed very quickly. Another thing what you can have is that the signal becomes like a line on one side. So that means it drifted that much, or most likely, so you calibrated it while it was drifting. And then when it's stabilized, when the signal is completely in different area. So if it's that much off, first you can still try to do manual calibration. And then afterwards, if it's still off, then just redo the wavelength scan, then do this manual calibration, and then you can continue with your experiments. So it's not a big issue. You can very quickly fix it while, yeah, just being in the sample dish. You don't really need to go back to the original dish. So yes. And the last video that I have from this part is how the signal looks like when we enter the medium. So you saw when we get out of the medium, the signal, I will start it again. Let's see if it works. When we go out of the medium, the signal becomes like a point because cantilever is facing down towards the fiber. That's why it looks like this, so nothing to worry. When you come back to the medium, as I did here, the signal goes back to where it should be. It's actually, yeah, it's nice. You can use this to know if you entered the medium already or not. So it gives indication. Also, if the signal is gone while you are doing the measurements, which can happen, it just means, it becomes like a point. It means your cantilever is in the wrong place. It's either stuck to the fiber or something like that, or you are indenting too deep into the sample. So that's why it's like a point, because it's just bending that much that there's no signal anymore. So the easiest, you bring the probe out of the medium and you bring it back in. Run liquid, pre-wet the probe, and it should go back to normal, and your signal will just come back to normal where it was. So that's what I meant by, yeah, this signal is basically your eyes. You know exactly what's happening. You don't need to even look at the probe, what's really there. Yes, so it's already 1 hour. So I didn't even cover yet the second part, which is about yeah, different fitting options, different indentation profiles. So as you all voted that we should stop after an hour, then I guess I should do that and then schedule another session for the second part. So then at the same time, we can cover all the unanswered questions the next time. And also, yeah, and cover the rest. However, I would like, as you are all still here, go to the last part. So now I'll have to quickly go through all the slides so you see them quickly. So this is all the material we will cover next time. It was still quite a lot. There are a few questions that I do want to ask you already. So the poll questions while you are still here about data analysis. So we would like to launch a new type of data software. So it will be browser based instead of the data viewer. What it could do is that we would provide you the cutting tools, which will be just online. So we will cut out the data of the indentation, such as approach, loading, holding phase, oscillation parts, and then unloading. And then you can just use any model that you like, that you maybe have, or you found in the literature to fit the data. Because there's so many, so we have Hertz, Oliver for our JKR and DMA, but there are so many other models that you could use that maybe are more appropriate for your sample, or that could maybe give you more information about the sample. So we don't have ability to implement all of these new models in the system. So that's why we would like to launch this, let's say, collaborative work, that we cut the data and you can just fit the model that you like. And you can also share the models between the groups. So for example, if one group has some very nice models, we can just share it with others and everyone can just very quickly use it on their data and see if it's better for them. So my question is, whether are you using data viewer as the main data analysis software, or you have your own custom data analysis code? And we are also looking test people. So if you would like to test out the beta version of Prova, that's the name of this browser, then yes, you can just say that you would like to test it out, and we will share with you the first version, and you can try to do some fitting there. So fitting will be based on Python, probably initially, and then later we would have other options as well implemented there. Okay, that's very encouraging. I see a lot of people who would like to test out Prova. That's great. And yes, very shortly about our vision of the future of mechanics to finish it up. So we see the growth of the use of the 3D cell cultures, such as hydrogels plus cells, organoids, spheroids, of course, and also building modular tissues for tissue engineering. So more complex, heterogeneous, rather than homogeneous materials. All of these samples should mimic in vivo mechanical microenvironment, not only on the cell scale, but also as a whole construct, in order for the cells to function properly. So we see the need that the mechanical characterization of these structures will be important. Now, these microtissues, I call them in general like that, will have to be grown in physiological environment, which could closely mimic which should closely mimic in vivo physiological environment. So it will require not only the standard incubation, so CO2, temperature, pH, and medium, but also control or even to measure other vital parameters such as oxygenation, maybe metabolic activity, conductivity. I don't know. It's yes, there are many parameters, and this we believe can be done through optical fiber interferometry, and we are going to look into that. Also, mechanical stimulation is no question will be needed to grow real tissues in addition to active perfusion rather than static medium. So this is our vision and where we are going with the Pavone, that we can provide such a platform where you can do all these things. Also, we see that the scale up of biofabrication and optimization of the workflows for biofabrication will be needed. So the reproducibility and also quality control of these large numbers of samples could be assessed through mechanical testing in addition to other tests, of course. And furthermore, the high throughput screening could use mechanics as a label-free biomarker, as you all know, to assess the state of the cytoskeleton or extracellular matrix when treated with different drugs, or even for diagnosis, such as in cancer and fibrosis. And we really believe that this is, this is going to grow and be more and more important. So we are very optimistic about the future, and we are going to be working hard to provide scientists with these tools that they need to build this future. Now, from your side, as you are actively working in this field, I would like to ask regarding the physiological parameters. What do you think is the most important? Because we have so many options, and we are thinking of building new sensors, and we are just curious from your perspective, what will be the important physiological parameters that you would like to either read out or to control directly in the sample, rather than just just assuming the value by incubator, let's say. So this gives us nice information, and maybe next year we can also launch additional modules with the features that you selected. Yes, so we are a big team. I wanted to put everyone in. So in one way or another, you might get in contact. So this is more application deep. We are actually 25 people, but these are the people who get in contact with customers. So we have very different skills, from salespeople and product managers like me, who perform demos all the time and thus measure all kind of samples. Also application specialists, software engineers, and actually people who have built the systems. So we can all help you. So yes, if you have any more questions or issues, then we are very much interested in helping you and going to that blue area where you can all say that our system is easy to use. Okay, so I think we are done. As I said, 1 hour, 15 minutes. I will send you all an email about the second part, where we will look into the questions that were answered already, but maybe I can go through them again. Then also look at the data analysis and different indentation profiles that would help you to set up the experiment. I could also answer some questions now that we're not finished. Someone asked, so in the chat, can someone copy the links to the resources? So it will be in the chat window. Then, yeah, I saw some people were using tissues. Do you know what is the stiffest tissue that was measured successfully? The stiffest side is a bit tricky. So we can measure 1 gigapascal. You can also measure a bit stiffer, but you can use this calculator to actually see how stiff can you go. So if you would use the stiff probe and very small radius, you can go up to 3 gigapascals, but I don't have such a data. You have to look through the publications if anyone worked on a stiffer sample. And also I see questions such as 12 times 12 matrix scan takes quite a long time, right? It's possible to make it fast. So I can do 12 by 12 in 8 minutes now. So you can choose very fast indentation profile without the approach time. So yeah, I can show next time how to set that up, a fast matrix scan. Using side mode with Chiaro, how long could the bead be? Could it be, say, 20 from the bottom cover slip? Slip line may be too large to get this low. Yes, so the cantilever is overhanging over the probe. So it's going to be the lowest point. So you can go with the probe down and then really indent something which is just at the glass slide, such as cells. So we have a group who is making this experiment. So hopefully we can share some data soon. We will actually write application on how to indent cells from the side. So yes. Yeah, so other questions, I maybe just send an email to everyone and share the questions and answers so we can learn from that. And if you have any questions regarding upgrades, please get in contact. Yes, it's end of the year, so you can still get a good deal for that. Okay, then bye everyone.